For decades, the Pentagon relied on a 74-minute window to detect a ballistic threat. That was the exact time required to pump volatile liquid fuel into the massive tanks of the Hwasong-18. On April 13, 2013, deep inside the dense canopy of the Taedong forest, that survival window violently collapsed to less than 15 minutes. The United States Space Force space-based infrared system satellites, staring down from geosynchronous orbit, saw nothing until the sky was already tearing apart. An 18-wheeled transporter erector launcher had seamlessly elevated a sealed thermal canister to a strict 90-degree vertical. Inside this armored tube rested the Hwasong-18, a solid-fuel intercontinental ballistic missile designed to fundamentally rewrite the mathematics of nuclear deterrence. This machine is not a weapon of prolonged logistical preparation. It is a pre-loaded coiled spring of geopolitical destruction waiting for a single electrical impulse. The initiation sequence begins not with a fiery ignition of the main engines, but with a violent mechanical heave, known as a cold launch system. At the reinforced base of the canister, a specialized solid propellant gas generator detonates. This preliminary controlled explosion does not propel the missile toward its target. Instead, it creates a massive acoustic and pressure wave expanding at supersonic speeds against the titanium baseplate of the missile itself. In a fraction of a second, this overwhelming pneumatic force ejects a 50-ton cylinder of carbon composite and high-explosive payload 30 meters into the air. To understand the sheer kinetic brutality of this mechanism, imagine popping a champagne cork. But that cork weighs exactly the same as a fully loaded M1 Abrams main battle tank and is being forced upward against Earth gravity in less than 1 second. The missile is thrust upward purely by trapped pressurized gas clearing the launch tube before the primary engines even awaken. This critical delay prevents the ferocious exhaust temperatures from instantly melting the transporter erector launcher below, ensuring the mobile vehicle can drive away to a bunker and reload for a second strike. The true engineering terror of the Hwasong-18 lies hidden beneath its matte black carbon fiber composite shell. Unlike its liquid-fueled predecessors, which relied on fragile, complex plumbing, thousands of interlocking valves, and highly corrosive liquid propellants, this new machine utilizes a solid propellant grain. Specifically, it is a highly volatile mixture of hydroxyl-terminated polybutadiene binder, ammonium perchlorate oxidizer, and microscopic aluminum powder. This chemical slurry is poured directly into the motor casing and cured under immense pressure into a dense, rubbery monolith. The carbon fiber filament winding process used to build the outer casing requires thousands of hours of precision overlapping to create a pressure vessel light enough to fly, but structurally capable of withstanding external forces equivalent to the crushing depths of the Mariana Trench. However, casting a solid motor of this terrifying magnitude is a metallurgical and chemical tightrope walk with no safety net. The internal geometry of the propellant block is not a solid cylinder, but is cast with a complex star-shaped hollow core to maximize the burning surface area. The margin for error is absolutely zero. If a single microscopic air bubble measuring just 1 millimeter is trapped inside the propellant during the lengthy curing process, the physical results are catastrophic. When the primary igniter flashes at the apex of the cold launch, the flame front travels down that hollow core. The solid fuel burns from the inside out, generating a staggering internal pressure of over 1,000 pounds per square inch and a core temperature exceeding 3,000 degrees Celsius. This is a thermal environment hotter than the boiling point of iron, capable of melting a standard commercial jet engine into liquid slag in less than 3 seconds. If that rapidly expanding flame front encounters a 1 millimeter air bubble, the burning surface area dynamically alters, causing an instantaneous localized pressure spike. The thrust becomes violently asymmetrical. In less than a blink, the internal pressure sharply exceeds the tensile strength of the carbon composite casing. The missile will not launch. It will violently disassemble itself into a cloud of shrapnel and unburnt fuel directly above the launch pad. But if the casting is structurally flawless, the ignition is a masterpiece of destructive thermodynamics. The solid core detonates mid-air, catching the 50-ton beast before gravity reclaims it. The sudden conversion of solid chemical energy into raw kinetic thrust subjects the airframe to a bone-crushing acceleration force. The exhaust plume, a blinding white pillar of burning aluminum oxide particles, burns so intensely hot it can completely blind the infrared thermal sensors of any interceptor missile attempting to lock on during the vulnerable boost phase. The Hwasong-18 accelerates vertically, tearing through the dense layers of the troposphere in a matter of seconds. The 50-ton beast has successfully cleared the launch tube and survived its own violent ignition. But escaping Earth gravity is merely the prologue. At Mach 5, the atmosphere transforms into a solid wall of concrete, and the second stage must detonate its explosive pyrotechnic bolts exactly at the microscopic edge of the stratosphere, or the entire missile shatters. The staging sequence is a violent mechanical divorce executed in milliseconds. At an altitude of exactly 50 kilometers, the atmospheric pressure drops to near zero. A network of linear-shaped charges and pyrotechnic fasteners embedded in the interstage ring detonates simultaneously. The 50-ton dead weight of the depleted first stage is violently severed from the accelerating upper section. Small retro rockets on the first stage fire instantly to push the massive empty shell away, preventing a catastrophic mid-air collision. Instantly, the second stage solid rocket motor ignites within this high-altitude vacuum, pushing the remaining payload toward orbital velocity. But raw thrust is useless without absolute directional control. This is where the thrust vector control system takes over. The solid rocket nozzles are not fixed. They are mounted on heavy-duty electro-hydraulic gimbals. These mechanical actuators physically pivot the blazing exhaust bell, steering a 20-meter-long cylinder, traveling at 15,000 kilometers per hour. To understand this mechanical nightmare, imagine trying to thread a microscopic needle while riding outside a bullet train. But the needle is on fire at 2,500 degrees Celsius, and any slight overcorrection will snap the airframe in half due to aerodynamic stress. Inside the guidance bay, a laser ring gyroscope spinning flawlessly detects millimeter deviations in the pitch, yaw, and roll, feeding hyper-fast calculations to the gimbal actuators. The Hwasong-18 does not fly a traditional flat ballistic arc. Flight data from its July 2023 test revealed a lofted trajectory. The guidance computer commanded the gimbals to steer the missile almost straight up into the cosmos, piercing the thermosphere and reaching a staggering apogee of 6,648 kilometers. This is not a mistake, but a terrifying mathematical demonstration. By shooting higher than the International Space Station, the missile proves it possesses the kinetic energy to achieve a standard horizontal range exceeding 15,000 kilometers. That radius places every single military base and civilian center on the continental United States well within the crosshairs. Once the third stage burns out, the final payload is released into the absolute zero temperature of the void. This is the re-entry vehicle. It does not fly to its target. It falls. Falling from an altitude of 6,000 kilometers, gravity accelerates the warhead to speeds exceeding Mach 20 or roughly 24,000 kilometers per hour. At this hypersonic velocity, the atmosphere is no longer air. It acts as a physical barrier. The blunt nose of the re-entry vehicle slams into the thickening atmospheric layers, violently compressing the gas molecules directly in front of it. This extreme hypercompression does not generate standard friction. It generates a localized bow shock wave that superheats the surrounding air into a glowing envelope of electrically charged plasma. The temperature along the leading edge spikes to over 7,000 degrees Celsius. This thermal environment is significantly hotter than the visible surface of the sun. It is a temperature that would instantly vaporize weapons-grade tungsten steel into a cloud of atomic dust. To survive this descent into hell, the warhead relies on an ablative heat shield primarily woven from a specialized carbon-phenolic composite. This engineering marvel is not designed to deflect the heat. It is designed to die absorbing it. As the exterior layers of the shield are exposed to the 7,000-degree plasma, they physically boil away, charring and peeling off into the slipstream, carrying the catastrophic thermal energy away from the nuclear core hidden just millimeters beneath. As long as the ablation rate perfectly matches the descent velocity, the payload survives. The Hwasong-18 is not merely a collection of advanced metallurgy and volatile chemistry. It is a solid-fueled geopolitical dead-man switch, capable of materializing from a hidden forest and delivering a localized artificial sun across the globe in under 40 minutes. If you want to dive deeper into the terrifying engineering behind the machines that shape our modern world, do not forget to subscribe to the channel and leave a comment below about which weapon system we should dissect next.